Suppose we have an object with mass m, and this object rests on a path, that is, on the origin of positive x-axis. And let us say we have an external agent with a constant force pushes this object to give it a distance. That is, the object picks up speed or velocity to the right-hand side with I unit vector. That is, as it moves. Now, what we have just seen was that this object had kinetic energy, or energy due to motion. It had energy of motion, and also momentum, an amount of motion. Now, we ask a very simple question, yet fundamental. For the same particle or the same object, when kinetic energy and momentum become equal, what are the conditions? Or in other words, when energy and motion come to harmony? Well, let us start by equating both expressions. That is, kinetic energy is equal to momentum. Thus, 1 over 2 mv squared is equal to mv. Provided that the mass is non-zero, that means the object exists. Okay, now we can cancel both masses on both sides. We get v squared is equal to 2v, or grouping we get v times v minus 2 is equal to 0. Then we get v is equal to 0 meter per second or 2 meters per second. Now you may ask, why meter per second? Well, it's because we follow the SI unit system, and you may get other units such as centimeter per second or any other units, but still, it's 2. So what we are interested in is this non-trivial value, v is equal to 2 meters per second. Regardless of the trivial case, which was v is equal to 0, we are interested in this value. This value. Why only that value? What's so special about it? What made it so? Why not any other value that makes kinetic energy and momentum to be equal? Alright. Now, to answer that, let's go back to mathematics. Suppose this is the positive x-axis and this is the positive y-axis. Let's say we have two functions intersecting. Y1 is equal to x, which is a linear, and y2 is equal to 1 over 2x squared, which is quadratic. Of course, they intersect at 2, 2 and 0, 0. Let's abandon 0, 0, which is the trivial case, but the 2, 2, or in other words, at x is equal to 2, they intersect. Now, we have a mathematical claim, and the claim is this: 1 over n x squared is equal to x, provided that x is equal to n. That means the denominator 1 over n, this n value, governs how and when, where these two functions intersect. Whenever, for instance, if we have 1 over 3, then at x is equal to 3, they will intersect. 4 at 4, 5 at 5, and so on. But that's in mathematics. It's abstract. What about in physics? In physics, we have already 1 over 2. That means it's already there. N is equal to 2. We didn't choose for it. But in mathematics, it's purely abstract, so we can choose any value n and we can play around with it. But in physics, it's not there anymore. So it's already predefined. It's 2. So that may tells us why kinetic energy and momentum become equal at that particular value, because of the nature of mathematics and also our nature, our physics nature. Okay. Furthermore, we may just plot both momentum and kinetic energy graphs. All right? They will intersect no matter what at some particular point. All right? And of course, that particular point, what I mean by that particular point is the y part, which is the kinetic energy and momentum. It may be any value, But nonetheless, it's still on speed when is equal to 2 meters per second. It's on that value. All right? So it requires that. Only at speed is equal to 2 meters per second, the intersection will happen. Okay? Now, we may be interested in why, or I should say we are interested in that fraction 1 over 2, why it did show up. Okay. Well, we know that kinetic energy is nothing but integral of momentum dv, or the integration of momentum of an object when it accelerates and picks up speed. We integrate it with respect to dv. What do we get is that, of course, kinetic energy is equal to 1 over 2 mv squared. Now, please, don't forget that I didn't forget about the 1 plus c constant of the integration. It's so trivial because we are not interested in the initial value problem, or the initial conditions. When speed is 0, then kinetic energy is also 0, so therefore c is equal to 0. Let's abandon that, let's ignore that. What we have now is just kinetic energy is equal to 1 over 2 mv squared. So again, we see this 1 over 2 appeared. That's telling us something. That is, of course, because of calculus. Because of calculus, we got that 1 over 2. But at the same time, it's physics. Not only calculus, but maybe our nature. Our universe works in this way. By accumulating energy and then dividing all of it by 1/2. What I mean by this is we could have kinetic energy is equal to mv squared, because both these expressions have the same units. So this 1 over 2 does not alter the consistency of the units, but the way how energy accumulates. So what I want to say is that we get to the conclusion that this 1 over 2 is so special. It's the nature's way to accumulate energy, or kinetic energy, along with momentum. All right? Because you see that even though mv squared or any other value multiplied by mv squared still gives us the same units. But for our nature, 1 over 2 is the valid case, is the valid option. Another conclusion is that kinetic energy always starts to show its explosion nature, its explosion behavior, because it's quadratic. Whenever we pick any value of the speed more than 2 meters per second. Because we know that kinetic energy is quadratic, so it will explode. At first glance, from 0 up to 2, kinetic energy is always behind. But then it becomes so sensitive if we pick any value bigger than 2 meters per second. Okay. Now, we may ask another fundamental question. What about the relativistic conditions? I mean, we know that in relativistic conditions, or in relativity, in modern physics, we have kinetic energy is equal to gamma minus 1, where gamma, it's the Lorentz factor, all multiplied by mc squared, and momentum is equal to gamma mv. We have no 1 over 2 fraction again, and there is no even 2. So, what about them? So what will be when we equate both of them in the relativistic case? Well, let's start. Let's do it. Of course, the calculation or the algebraic manipulation will be messy, but I'm going to show you how it looks like. So we start by equating kinetic energy is equal to momentum. Gamma minus 1 mc squared is equal to gamma mv. And from here, it will get messy, but you may pause the video and you do the math for yourself and see it, because otherwise it will just lengthens the video. So here it is. Right here. You may pause it right here and see it yourself. The last equation, v multiplied by 1 plus c squared is equal to 2c squared, is what it gives us an interesting result. That is, if we solve for it, we get v is equal to 2c squared divided by 1 plus c squared, which is fairly close to meters per second. So interestingly enough, it showed up once again. But what is so important here is that why this value again? As a matter of fact, 2 meters per second, it's not even in the relativistic region. It's in the classical region. So perhaps it tells us that we should revert back to the classical sense or the classical case to understand this value. Because this 2 meters per second is not even close to the speed of light. Alright? So it's strange. Again. Furthermore, I gotta stop somewhere and ask you, what about in terms of rotational mechanics? I'm gonna stop it here and leave it to you. What are your ideas? What are your thoughts on it? Please, if you do, comment in the comment section down below, and I'll be happy and appreciated to see and examine those ideas. As always, thanks for watching.